I don't remember where I saw this question, but I thought it's one hell of a meaty boy. So let's get into it. Let's first recall the Fourier transform convention, which is fk equals 1 over root 2 pi integral of minus infinity to infinity of fx e to the minus I kx dx. Get used to that. You've got to remember that. Since fx equals 0 is outside of the modulus of x that is less than or equal to 1 over m, we can now change these limits. So the limits would then become fk over root 2 pi, and it would be 1 over m and minus 1 over m. We now know that fx is mx, so let's plug that in. So that is replaced by that. And then it's e to the minus ikx dx. This m can obviously be pulled out because it's just some constant or some value. So that can disappear and it would go there. And that means we're just dealing with x e to the I minus I kx. And that's going to be the integration that we're dealing with. That is going to need integration by parts, which should be fairly simple for you all. So u equals x, u dash equals 1, dv dx would equal e to the minus ikx, and therefore v would be e to the minus ikx divided by minus ik, uv minus the integral of v du dx. So you're going to get x e to the minus ikx divided by minus ik minus the integral of e to the minus ikx minus ik, and then 1 multiplied by 1, u dash is there, dx. We now have to integrate this again, and you're going to get minus x e to the minus ikx all divided by ik plus, you're going to get, what is it, 1 over ik dot e to the minus ikx over minus ik. But obviously we're nowhere near finished. We can now see that e to the minus ikx is common on both sides, so let's pull that bad boy out. So e to the minus ikx is out, and you're then going to get minus x 1 over ik squared. And we know what were the limits that we set is 1 over m and minus 1 over m. So we can apply these limits to our final integral. So you're going to now get e to the minus ik over m minus 1 ikm minus 1 over ik all squared minus e to the ikm, minus ikm, and I've obviously not left enough space to pretend that that's multiplied to this, so it's going to be 1 over ikm minus 1 over ik squared. But we know Euler's identities because this is looking suspiciously Eulery, is that a word? Euler? Oh, I don't know. So then we have e to the minus I theta plus e to the I theta, which equals 2 cos theta. And then there's another one where instead of there being a positive here, there's a negative. So that's going to be e to the I theta, which equals minus 2i sine theta, where theta obviously equals k over m. So if we now expand and simplify this all together, you're going to now get, actually I'm not going to expand and simplify this totally, it's just going to be a waste of time. You know how to do it. I'm going to presume that you've expanded and simplified it and now substituted in these identities. So I'm going to get minus 2 cos k over m divided by I km plus 2I sine k over m divided by ik all squared. But we now know minus 1 over I equals I, and ik all squared is just minus k squared, because you should know that I squared equals minus 1. So we can now start playing around with these i's. There's an I in the denominator right here. There's an I squared here. There's an I up here. We don't want any of them. We hate them. And obviously, please remember, we have this m over root 2 pi here. So fk would then be m over root 2 pi, and you would get 2i, because remember, this minus I here goes to the top, cos k over m divided by km minus 2i minus 2i, because remember this has become I squared, sine k over m divided by k squared, and pretend there's a lovely closing bracket, but I couldn't fit it out. We can also now pull out this I, so fk would equal mi over root 2 pi cos, oh actually no, I pulled out the 2 as well, didn't I? Yeah. Pulled out the 2i. But actually no, the m's can cancel out as well. Yeah, look, there's an m here, there's an m here. So the m's can cancel, so you're going to get 2i, and I've simplified for m, so you're going to get cos k over m over k minus m sine k over m over k squared. So that's the solution of this Fourier transfer. Unbelievable. Quality work right there.